So moving on, some other features that we can get from these stress strain curves. We have the highest data point on the curve. We mentioned that a little bit ago. So the highest point on the stress strain curve is the tensile strength, sometimes emphasized as ultimate tensile strength, meaning the highest value registered. So this might be the most amount of force that we could apply to the object, regardless of if it changes shape or not during the test work. Okay, so largest y-coordinate on the graph is a nice way to recognize that tensile strength value. Yield strength. This is the one I alluded to just a moment ago, where we were going to register a small amount of permanent deformation. So the convention is to look for 0.2% permanent deformation. Okay, so we saw that percent elongation was the strain times 100%. So thinking about the x-axis values here, moving the decimal point over 2 units gives me percent elongation. So that is, this is 0.2, this is 0.4, this is 0.6, this is 0.8, this is 1% elongation. Okay, so we're looking for 0.2% on there. So here you can see that this value here represents that point. So in the experiment where we load the specimen, we're pulling on the specimen. If we were to end the loading experiment before even moving outside of the elastic portion of the graph, like a true elastic, the matter would return to its original shape and we would register no size change. So that is L final minus L initial is equal to 0. There's no permanent deformation there after the test, LF. However, when we load past the elastic portion, we get into the plastic deformation region. This is where some permanent size change occurs. And if we extended our experiment, we would return to 0 load, so climbing down the y-axis, return to 0 load. Notice that our unloading curve is parallel to our modulus because the material is still the same. And we would intercept the x-axis here at a non-zero value. So when this non-zero x value is the 0.2% elongation, this is how we kind of think back to it, the amount of stress that led to that, and this is our yield strength. Okay, so saying that all in one sentence, it is the stress necessary to generate 0.2% permanent deformation on the object. Okay, so with those sort of experiments on matter, we've actually already covered the idea of elastic recovery. And so if a specimen is loaded beyond the elastic limit of the material, we can expect it to undergo some permanent deformation. We saw that. After unloading the matter, the elastic strain will be recovered. Okay, so we saw that a moment ago. So here, as we return to no load, we're climbing down, dropping the force on the object. And of course, there's going to be some strain recovery. The strain recovery here that takes you to the x intercept, that is the elastic recovery. Okay. Okay, so that amount, elastic recovery, can result in elastic strain. So where we've recovered, we've kind of come back a little bit. So the elastic strain is here. And then the permanent strain would be over here. Okay, so that is now because the x-intercept for the material is not at the origin of this graph, that we know that there's some permanent strain on the object due to loading past the elastic limit of the material. Okay. So in other words, permanent strain plus elastic strain equals the total strain, which was the x coordinate taken here to the end of the experiment. Okay, another feature of these graphs is toughness. So we saw a moment ago when we looked at work equals force times distance on our spring, that we saw the area in the graph was important there. Here we have an important analogy to draw where toughness is going to be the energy value, similar to the energy units used for work. So the energy required to break a unit of volume of matter. Okay, so we get this by multiplying kind of y information times the x information to get area under the curve. Okay, so the area under this blue curve represents how tough this material is. So this ceramic doesn't have as large an area under its stress strain curve, and so it's not very tough. Metals, as you know, are very tough. You have to apply a large amount of energy to break them. And so the area under this curve is represented here by the green. And there's a large area there, so we would regard metals as being very tough. And then those materials that are not as stiff and don't give us large tensile strength values and lower fracture points, like some pure polymers, are regarded as not very tough as well, because their area under the curve is very small as well. Okay. So when a material is not tough, we can equate it as being kind of brittle. And if a material is ductile, it can deform, and we see that here for the polymer material. Okay, another thing that happens during these test work, as I alluded to earlier, is this test specimen will deform. And so what is known as in metals, that as one is climbing the stress strain curve past the elastic portion into the plastic deformation region of the curve, once we transition past the tensile strength value, the highest point on the curve, that necking starts to occur. So this is the reduction in the cross-sectional area of the specimen, as you see here, where the specimen used to be cylindrical, and now we see an obvious necking here where it's pinching in. So this necking begins right after that ultimate tensile strength value. Okay, so necking here is as we transition from this region over to this region. And you see that in this diagram. As you think about it, here if the necking is registered now, our cross-sectional area is reducing. So all of the tensile force on our sample is now focusing into a smaller area than what we had originally, which is represented by matter up here, where there is no necking, and that's very close to A naught. So notice that cross-sectional area is going to decrease. And so all the force applied is focused into a smaller area. And now we're going to register a lot of deformation. Okay, so that explains why we kind of drop the curve very quickly. We no longer need as much force to trigger increases in deformation because the cross-sectional area is reducing due to necking. So the neck acts as a stress concentrator, allowing us to drop the force and still move further to the right on the x-axis in the strain axis direction. Okay, so looking at a lot of the properties that we've covered density, we've covered stiffness, that was Young's modulus. How about strength, the ultimate tensile strength? So these are some of the highest points on the stress strain curves for these materials. And then toughness, how tough a material is, area under the curve. We see all of those same materials compared here. And so most of the general pattern to where materials are doesn't change that much. You'll notice that ceramics are very stiff, but as you might expect, their ultimate tensile strength is a little lower compared to some other materials. So notice that shifts a little bit down when you compare to how it competed with metals as far as stiffness. When we go to resistance to fracture, the toughness of the material, that's where ceramics really kind of lag behind relative to other materials, and again, metals sort of lead the way there. And as we consider the case for composites, we saw that they were competitive in their stiffness to most materials, so competitive with ceramics and competitive with metals. And then as we go to tensile strength, the highest data point on the stress strain curve, those remain competitive with metals and ceramics, and it's only the woods that kind of act to bring the range up for composites across this tensile strength property category. Same thing said for the resistance to fracture, here represented as toughness value. And you'll see that the reinforced composites, both carbon fiber and glass fiber, remain competitive with metals. So it's for all of these reasons that you know that carbon fiber and glass fiber reinforced composites are a good material selection choice for things like aerospace and other transportation sectors where we need to manage mass but achieve the same strength to the ultimate material when it's put in service in those transportation sectors. So things like carbon fiber tubing for bicycles are a good example of the CFRC, where we can go to lower mass but still be as resistant to fracture in the toughness category and be as stiff as metals as well.